Atoms are made up of a nucleus containing protons and neutrons, which is surrounded by electrons. This will be a very familiar image to you, but unfortunately it's a little more complicated than this famous image suggests. Atoms are made up of energy levels, also called shells. These shells contain subshells, which contain orbitals. These orbitals are the space the electrons are found in. Let's begin with the subshell. There are 4 types of subshell: S, P, D, and F. The shell number dictates how many of these subshells there are. Each shell is given a number called its quantum number, n. In short, this number represents how close to the nucleus the shell is, and hence how much energy it has. The first shell, whose quantum number is 1, only contains one subshell, the S subshell. The second shell contains 2 subshells, S and P. This pattern continues up to the 4th shell. Each subshell is made up of orbitals. There are different types of orbitals that take on different shapes. The S orbital is spherical. The P orbital is dumbbell shaped. As you go through the orbitals, the shape becomes more complicated. Each orbital can only hold 2 electrons, and these electrons have to spin in opposite directions. This is due to something called Pauli's exclusion principle. Each subshell contains a different number of orbitals. The S subshell contains one S orbital, so is able to hold 2 electrons. The P subshell contains 3 P orbitals, so it can hold 3 times 2, or 6 electrons. The D subshell contains 5 D orbitals, so holds 10 electrons, and the F subshell contains 7 F orbitals, so holds 14 electrons. Let's see how this affects the number of electrons each shell can hold. The first electron shell, sometimes called the K shell, contains one S subshell, so is only able to hold 2 electrons. The second shell we know contains one S subshell and one P subshell. Therefore, the second shell can hold 2 electrons in the S subshell and 6 electrons in the P subshell, for a total of 8 electrons. The third shell contains an S, P, and D subshell, for a total of 18 electrons. And finally, the 4th shell contains an S, P, D, and F subshell, for a total of 32 electrons. Let's see how these shells fill up using the example of oxygen. Oxygen has 8 electrons. The electrons fill up the sublevels in the following order. The S subshell of S1, called 1s. The notation 1s1 indicates there is 1 electron in the S subshell of shell 1. 1s2 indicates there are 2 electrons in the S subshell of shell 1. Next to fill is the S subshell of shell 2, 2s, which can hold 2 electrons, followed by the P subshell of shell 2, 2p, which holds up to 6 electrons. So the final 4 electrons in oxygen will occupy this subshell. The notation 1s2, 2s1 shows us there are 2 electrons in the S subshell of the first shell and 1 electron in the S subshell of the second shell. One s2, 2s2, 2p4 is what we call an oxygen atom's electron configuration. It's a way of showing where all the electrons in an oxygen atom are found. Have you ever wondered why the periodic table is shaped the way it is? It's to do with electron configuration. The periodic table can be split up into blocks, the S, P, D, and F blocks. Sound familiar? An element's position in the table tells us a lot about its electron configuration. The row it's on tells us how many shells it has, and the block it's found in tells us the subshell its last electron is found in. So let's return to our example of oxygen. How can we use the periodic table to determine its electron configuration? Like so. As you move through the periodic table, you'll see that we fill up the shells. You'll notice that as you add to the shells, you find yourself in that block. Atoms in P block are filling up their P shells. Let's look at the position of oxygen and its electron configuration. It's in the second period, 2, and it's the 1, 2, 3,
fourth element in p block. Hence, its electron configuration ends in 2p4. Given that we know it ends with 2p4, we can fill the rest of the shells that come before 2p to give us 1s2, 2s2, 2p4, its electron configuration.
Let's take a trickier example, like iron. An iron atom has 26 electrons. These electrons fill up the shells in the order we'd expect. 1s, 2s, 2p, 3s, 3p. However, after 3p, things don't quite stick to the pattern. We would expect that 3d would be the next subshell to fill. However, it's actually 4s that fills first. This is because the 3d orbitals are at a higher energy level than 4s. Once the 4s subshell is filled, the 3d begins to fill. Given an iron atom's final electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Again, the periodic table shows this. Here we see that the D block of elements begins at 3d, despite being in the fourth row.
The shells fill up in the same order: 1s, 2s, 2p, 3s, 3p. And notice how the 4s block elements come first, so the 4s subshell fills first. We end with iron as the sixth element in block 3d, so fill up all the shells beforehand to give a final electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6.
Another way to visualize the filling of the subshells is on an electron energy level diagram. This diagram shows the subshells and their respective energy levels. Note that the 3d subshell is found higher up than 4s, due to having more energy. Each box represents an orbital found in that subshell. An electron will always fill the lowest energy subshell first. So we effectively fill in the diagram from the bottom to the top. Electrons are represented by these arrows. If we remember from earlier, the electrons in an orbital have to spin in opposite directions, so we show this using opposite facing arrows. Here we can see the electrons spread out before doubling up. This is because of something called Hund's rule. It states that every orbital in a subshell is singly occupied with one electron before any one orbital is doubly occupied, and all electrons in a singly occupied orbital have the same spin. What this basically means is that when completing electron energy level diagrams, add one up-facing electron to each orbital before pairing them off. Let's return to our example of oxygen. It has an electron configuration of 1s2, 2s2, 2p4. So let's begin filling the diagram.